Okay, this is a video on the simplex algorithm. I'm going to assume that you know nothing of simplex, but yet you do know of linear programming and how to solve two-dimensional problems graphically. What I've got here is a two-dimensional linear program, and it's two-dimensional because there are only two variables, x and y, which means this can be solved graphically. And as I go through the simplex algorithm, on the right-hand side over here, we can see that I have solved it graphically, or at least I've drawn the graph without necessarily solving it. But the simplex algorithm can be applied to this as well to give the optimal solution. And simplex is useful because it allows us to apply it to high dimensional situations. Three-dimensional problems can be graphed. Each constraint will be a plane, and the feasible region will be a volume. And again, because it's linear programming, the optimal solution will lie on a vertex. But it's very complicated because you need to solve multiple sets of simultaneous equations to find the vertices. And even when you do that, you then got to make sure that they are in the feasible region. So it's much better to use a simplex for three-dimensional problems. And when you get to 4 and higher, you can't solve them graphically at all. So simplex is necessary. So what we do is we first take these two constraints here, and we write them as equations by introducing two new variables. So instead of saying x plus y is less than or equal to 10, I'm going to say x plus y plus a new variable, which I'm calling s1, equals 10. And what this variable is called is called the slack variable. It takes up the slack that x and y don't make up to get to 10. Okay, it gives us an equation. And equations are easier to work with than inequalities. Do the same thing for the second inequality, and we end up with this situation. At this point, I will point out that simplex will only work in its current stage if the origin lies in the feasible region. So if this is a greater than or equal to constraint, we cannot use simplex in its current form because the origin is not satisfied by that inequality. We'll move on to two-stage simplex a bit later on, so I'll do another video on that. And then this one here, I can rearrange it. P minus 3x minus 5y equals 0, just so that all of my variables on the left-hand side of the equation, and then I just have numbers on the right-hand side of the equation. And that allows us to put the linear program into what is called tabular form. And simplex algorithm doesn't work graphically, it works in tables. So we're going to have lots and lots of tables. In the examination, the tables will be drawn for you. You just need to fill them out. So I've drawn out the tables already. And what I'm going to do, I'm just going to pop these three things into the table. So I've got an objective function and then two constraints. And I'm going to put them in. So it's 1p minus 3x minus 5y. No slack for that one, no slack for that one, and the right-hand side is currently 0. Okay, so that's this line here is in my table by counting off how many of each of the variables I have. The second one will be no p and no s2. So no p, no s2. I have an x, a y, and an s1, and that equals 10. And then the second constraint is 1x plus 3y, no s2. Sorry, no s1 plus an s2 gives 18. So that is what is called my initial Tableau. Okay, initial Tableau, and that's the Tableau you start with before you complete any iterations of the simplex algorithm. So once you've got your tables down, those are the instructions you follow. So you choose a pivot column, you carry out the ratio test and choose a pivot row. You then pivot, and then you repeat if necessary. Okay, so those are the 4 steps I'm going to be following, well, the 3 steps, and then repeating them as appropriate. And I'll talk you through each step as we get there. So first of all, is to choose a pivot column. Now, what this table represents is currently x and y are both 0, because these are what we call the basic variables, because these are the columns that I refer to as being full of junk. In other words, they are not full of lots of zeros and 1, 1. Okay, like this column this column, and this column. These three columns are referred to as the non-basic variables. And what this system represents is essentially three equations in 5 unknowns. So 1, 2, 3 equations, 1, 2, 3, 4, 5 unknowns. So we have what's called 2 degrees of freedom. We can choose 2 of those columns to be whatever we want. So in this case, it makes sense to choose x and y to be 0. That leaves us with p equals 0, s1 equals 10, and s2 equals 18. We are at the origin, x and y are both 0. But obviously the solution is not maximised, okay, because here p is 0. And we can see that p is 0. And that's no good because there are solutions in this feasible region where the solution is not 0. It's greater than 0. So we've not optimised the problem. We're just starting. And Simplex always starts at the origin. Now what we do is we choose a direction to move in. We can either choose at this stage the x direction or the y direction. And the reason why we can choose those is because these are the 2 elements that are negative in the objective row. So if there are negative elements in the objective row, then we can make an improvement. So there's a minus 3x there, there's a minus 5y there. Therefore, we can move in either of those 2 directions to improve our solution of 0. So I'm going to choose to move in the y direction. And typically, unless you're told otherwise, you will choose the most negative value in this objective row. So minus 5 is more negative than minus 3, so I'm choosing the minus 5. So that's what I'm choosing. If you have 2 that are the most negative, you can choose arbitrarily. It doesn't matter which you choose. We then conduct what's called a ratio test. Now, a ratio test is carried out on all the objective rows. So the objective rows are these 2. And what we do for the ratio test is we take the right-hand side and we divide it by the value in the pivot column that we've just established. So 10 divided by 1 in this case is 10, and 18 divided by 3 is 6. So in the y direction, we can either move 10 or we can move 6. And from the ratio test, you choose the smallest positive. So from the ratio test, we choose the smallest positive. Why? Well, what this says is I'm either going to move 6 or 10 in the y direction. If I move 6, I'll move from D to A. I'm still in my feasible region. But if I move 10, I'm moving from D to this point here. So by choosing the bigger value, I would have left my feasible region, which is no good. We want to remain within the feasible region. We don't want to leave it. So we can only move 6 in the y direction. So we choose the smallest positive. Don't choose any zeros because that just means you're going to stay where you are. There's no point in doing that. And don't choose any negatives because it means that you will be leaving the feasible region in the other direction. It's not really applicable at the first stage, but once you've done a few iterations in, sometimes you get negative values here. Don't choose those because you'll be going backwards. Okay. So choose the smallest positive from the ratio test. So in this case, that is the 6, and that chooses our pivot row. So we have our pivot column, we have our pivot row, therefore this one here is referred to as our pivot. Okay, that is our pivot for the first iteration. So what we do now is we carry out a series of EROs, EROs, elementary row operations. And we carry out a number of EROs to make this column look like what this column currently looks like. So we want to make this a pivot column. So we want to make this 0, 0, 1. That's the idea. The other pivot columns will remain as pivot columns. So this one here is a pivot column of the middle one. So that's going to be 0, 1, 0. And P will always be 1, 0, 0 because you never pivot on anything on that row. So that will always be 1, 0, 0 for the entire algorithm. So that leaves us then with 9 values to figure out. Now, the EROs that we use are we can multiply rows by a constant, which is obviously allowed because each row just represents an equation, so that's fine. And we can add rows to rows, which again, thinking about what these represent, they are just equations. So again, this is completely allowed. So those are the 2 EROs we're going to be using. There is another era where you can swap rows, but you don't need that for Simplex. So to make this then a 1, we take this whole row and we're going to divide it by that pivot value. So I'm going to divide it all by 3. So that 1 is going to become a third, that 1 is going to become a third, and this 18 is going to become a 6. Okay, that's just taking that whole row and dividing it by 3. Now what I'm going to do is I'm going to take multiples of this row, this row, add or subtract multiples of this row to make this value 0. So I could refer to that as row 1, row 2, and row 3. Therefore, I'm doing row 2, subtract a third, row 3. Or row 2, subtract the pivot row. Either way, I want to make this value 0 here. So 1 minus a third times 3 is 1. 1 minus a third times 1 is 2/3. 1 minus a third times 0 is still 1. 0 minus a third times 1 is minus a third. And 10 minus a third times 18 is 4. Yeah. Okay. Now this top row, I want to do that plus excuse me, plus 5/3 the bottom row, or I could say I want this row plus 5 times the bottom row. So minus 3 plus 5 times a third is minus 4/3. Minus 5 plus 5 times 1 is 0. 0 plus 5 times 0 is 0. 0 plus 5 times a third is 5/3. And 0 plus 5 times 6 is 30. And we end up here. And what hopefully you can establish is that this one and this one are now my basic variables. So those are set to 0. And P, Y, and S1 are non-zero. P is now 30, S1 is 4, and Y is 6. If Y is 6 and X is 0, then we're at this point here. And the P value at this point is 30. Okay, you can check that with the original linear program. But we're not at the optimal vertex yet. And I can tell that because there's a negative value in my objective row still. Okay, so because of that negative, it means an improvement can still be made on P. We want to improve P as much as we can so that we arrive at the maximal vertex. So therefore, because it's negative, we're not at the optimal vertex, therefore I need to do another iteration of Simplex. So that is now my pivot column. I carry out, again, a ratio test. Okay, don't apply the ratio test to the objective row. 4 divided by 2/3 is 6, and 6 divided by a third is 18, and I choose the smallest. So I'm either going to move 6 in the x direction, or I'm going to move 18 in the x direction. So if I move 6, I'm actually going to move down to here. If I choose 18, I'm going to move down to here. 18, again, you can clearly see is shot past the feasible region. So I only want to move 6. So therefore, that is the row that I choose, and that is my pivot in there. Now that I've chosen my pivot column and my pivot row, I pivot. So I'm going to take this whole row and times it by 3 on 2 to make that pivot value 0. Make that pivot value 1. That's going to be 3 on 2, that's going to be minus a half, and that's going to be 6. And now add and subtract multiples of this row to the other 2 rows to make everything else in that column 0. So 0, 0, that will always be 1, 0, and this is going to remain 0, 1 because it's the other pivot. So I'm going to do that subtract 2 times that. So that subtract 2 times that, that subtract half times that. So I'm going to do that subtract half times that is minus a half. That subtract half times that is third plus a sixth is a half. And that subtract half times that is 4. This one here, I'm going to do that plus 2 times that to make the 0. So that plus 2 times that plus 2 times that is 2. That plus 2 times that is 3/3, which is 1. And that plus 2 times that is 38. Okay, so that is my second iteration of Simplex. Just to decide where we are, S1 and S2, they are both basic variables, so they are both 0. These three are my non-basics, and we can read off that P is 38. Okay, P is 38. X is 6. And Y is 4. And we are at my optimal vertex because there are no negative values in the objective row. Okay, nothing negative in there. Therefore, I'm at my optimal vertex. And that is my optimal solution. X is 6, Y is 4, and P is 38. Solving it graphically, we would arrive at the same solution here. Is my optimal vertex. S1 and S2, the significance of them both being 0 means that we lie on those constraints. So S1 was originally the constraint, the slack variable for the first constraint, this one here, so that means there's no slack left. So we are lying on this constraint. 4 plus 6 does indeed equal 10. The fact that S2 is also 0 says that we also lie on this constraint. And we can see that 6 plus 12 is indeed 18. So there's no slack left in this constraint. Graphically, what's going on? Our solution is where these two constraints intersect. It's not always the case that the slacks will always be 0 at the end. Okay, sometimes there will be slacks, particularly if you have more constraints than you do dimensions to the problem. I will do a couple more examples for Simplex, just because there is a lot going on in Simplex, and I'm aware that it's very easy to make mistakes. So we'll do a couple more examples, and then I'll also do two-stage as well. Thank you.